a new year of the One World Combinatorics on Words seminar. So we're very happy to see you all again and to start up the seminar again. So our speaker today is Shuo Li, who's at the Université du Québec à Montréal, and he's going to speak to us about the number of squares in a word.
Okay, thank you for the introduction. Hello, everyone. So as it is introduced by Najat, the topic of today is about counting number of squares in a word. And it is a joint work with Sandra Brelek, Francisco Dawes, and Alice Vandal. So, well, okay. So first of all, let me fix, sorry about that. I don't know why. Sorry about that. Okay. So first of all, let me fix some definitions. By word, I mean a finite concatenation of letters, and the word sometimes also called a string. And the length of word W is the total number of letters appearing in this word. Well, for a given word W, its alphabet would be defined as a collection of all its distinct letters appearing in this word. And the factor of W will be defined as a finite string of consecutive letters appearing in this word W. So once we are given a word, people are interested in studying the different patterns appearing in this word. By patterns, we may list several of them, such as the palindromes, sigma palindromes, squares, etc., etc. Here, let me just give you some quick definition of some patterns that I would talk about later. By palindrome, I mean a word which equals its reverse. That means if W is a palindrome, then it is the same if we read this word from left-hand side to the right-hand side, and from right-hand side to the left-hand side. Well, by sigma palindrome, we mean a word which equals its reverse under some type sigma, where sigma will be an evolution on the alphabet of W, satisfying the condition that sigma square equals identity. By square, I mean a word that we can cut it into two equal parts, which means its first half part will equals its last half part. Well, once we define different pattern in a word, people are interested in counting the number of patterns in a word. If we let PW, P sigma W, and SW denote respectively the number of distinct palindromes, sigma palindromes, and the squares in word W, counting the empty word. So the empty word are considered as a palindrome, sigma palindrome, as well as a square. Then for the PW and the P sigma W, they are all upper bounded by the number by the length of W plus 1. Here the plus 1 refers to exactly the empty word. So this two inequality holds because of the following facts. In fact, if we are given a word, and if we want to add a letter at the end of this word, then we will be able to create at most one new palindrome as well as a sigma palindrome. So if we do it recurrently, then we will get these two upper bounds. Well, the things for square words are more complicated, because for a given word W, if we add one letter at the end of this word, sometimes we may able to create two new squares. So from this point of view, the SW can only be bounded by 2 times the length of W plus 1. However, when people trying to construct words with many squares, it seems that the upper bound of 2 times the length of W plus 1 can never be achieved. In fact, this problem has been first considered by Franco and Simpson in 1998. And when they tried to find words with many squares, they succeeded to find the following example. They define the sequence Wi as follows. First of all, they define sequence Qi in this formula, where 0 powers I means there exist I consecutive zeros appearing in the string. So if we take I equals 1, the Q1 would be 0, 0, 1, 0, 1, 0, 0, 1. If we take I equals 2, the string will be 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, etc., etc. And to define their sequence Wi, the ith term of this sequence is defined to be the concatenation of Q1, Q2 until Qi. So when they consider the sequence Wi, they find that for each term of Wi, the length of this word satisfies this identity, where the number of distinct non-empty squares of Wi satisfy this identity. Here by S star W, I mean just the number of distinct non-empty squares appearing in W. So in this case, we don't count the empty word. So with these two formula, we can make the following observation. In fact, the SWI is merely smaller than the length of WI, or more precisely, the S star WI equals the length of WI minus something in the order of square of WI. So it seems that we cannot do better. We cannot find the word with small squares. So Franco and Simpson conjectured that for any finite word W, S star of W should be upper bounded by the length of W. Well, this conjecture has received many attentions from different people, and the upper bound of S star W has been improved several times. It was first proved that S star W is upper bounded by 2 times the length of W, and after that, I improved this upper bound to 2 times of the length of W minus something in the order of log of the length of W. And let me improve this upper bound to 95 over 48 times the length of W. This and theory improves this upper bound to 11 over 6 times the length of W. And after that, theory himself improved this upper bound to 3 over 2 times the length of W. Well, as new result, we can prove, in fact, that the S star of W can be upper bounded by the length of W minus the size of this alphabet. And if we count the empty word, so the W will satisfy this indication. So how can we achieve this result? Well, the proof is, in fact, not difficult, but we will have to investigate some topological properties of the Jody graphs of the word W. So first of all, let me recall the definition of the Jody graphs. If we let W be a finite word, then for any integer I bounded between 1 and the length of W, we let I denotes the set of length I factor of W, and we let Ci denotes the cardinality of Wi. Then the S-root graph of W is an oriented graph, such that its vertex set is the set of words of length is the set of length I factors of W, which is exactly the Li, while the H set is the set of length I plus 1 factors of W, which is I plus 1. HE pointing from V1 to V2 if and only if V1 is a prefix of E, where the V2 is a suffix of E. So for those who are not familiar with this definition, let's consider an example. If we let W be a word like this, then the third root graph of W should be like this. So we can find all the length 3 factor of the word W on the vertices and all the length 4 factors of W on the edges. 2 vertices are connected by edges, by edge. For example, let's take a look for this 2 one. These 2 vertices are connected by this edge, if and only if the first one is the prefix of the edge, where the second one is the suffix of edge. And we do it, etc., and we will get a graph like this. So once we define our rosy graph, we can study some properties of these graphs. In fact, first of all, for the graph gamma I, in fact, the number of vertices on this graph is exactly Ci, where the number of edges on this graph is exactly Ci plus 1. Besides of this, we can see that all the rosy graphs of the word W are weakly connected, and the rosy graphs contain some cycles and sequences, where the square factors in W can be recognized with the help of sequence. So here, let me just clarify what I mean by cycles and sequence. A cycle, or more precisely an elementary cycle, is a closed chain of distinct vertices and distinct edges, where an elementary sequence is a closed path of distinct vertices and distinct edges. Here, let me just show you 2 graphs. So both of them are elementary cycles because they are closed by chains, where just the second one is a sequence, but not the first one, because the second one is closed by a path, where for the first one there are actually 2 paths, but none of them is closed. So that's the difference between a cycle and a sequence. A sequence is definitively a cycle, where a cycle may not a sequence. Well, there exists a well-known theorem, graph theory, which states as follows. The number of independent elementary cycles on graph G with p-connected components is given by the cyclomatic number chi G, which is defined to be the number of edges minus the number of vertices plus the number of connected components. As a corollary of this theory, for a given word W, then the number of independent elementary sequences on graph gamma I should be bounded by Ci plus 1 minus Ci n plus 1. So here, let me show you how the sequence can help to identify squares. Let us take X to be a primitive. And in this example, I will take X to be AAB, and in fact, the argument I will make works for almost every primitive word. If we let W to be a finite word contain X square, then in fact, we can find easily a closed path which goes through the all conjugate of the word X, and it returns to itself. So this closed path will form the sequence like this, and this sequence will be found on the rosy graph with index of the length of X. So in our case, if we let x equals AB, then we can find this this secret on the graph gamma 3. And so the word x square can be associated with this secret. Well, if there exists another square factor of w, y square, such that y is a conjugate of x, then besides of the first secret, we can find the similar secret on the next rosy graph, such that the vertex set of this secret is exactly the H set of the previous one, and they are connected one by one to form a secret like this. And if there exists z square such that z is a conjugate with x and different from y, then we can find similarly a secret like this on the next slide, on the next rosy graph. So here is the graph 5, such that the H set, the vertex set of this graph is exactly the H set of the previous one. And we can do it, etc., etc. Now, if the word x powers 4 appears in W, then besides of the secrets represented as above, there exists another secret like this. So the edge side, so the vertex side of this graph are the conjugates of the word AB powers 3, and they are connected one by one by a closed path. And if there is a word of type ABA powers 4, so ABA is the conjugate is X, and in this case we can find a similar rosy graph on the next similar secret on the next rosy graph, which is on gamma 10, such that the vertex side of this graph is exactly the H side of the previous one. And we can do it, in fact, etc., etc. At the end, in fact, we can find an injection from the non-empty square factors of W into the secret on the rosy graphs of gamma I. And if we denote this injection by phi, in fact, we can see we can see some more things concerning this function. In fact, we can prove that all the images of the injection phi are small secrets. Here, let me just clarify what I mean by a small secret. A secret on the rosy graph gamma I is called small if and only if it's the firstly an elementary secret. Secondly, the size of its vertices, the number of its vertices will be the number of its edges, and will be upper bounded by the index of the rosy graph, which is I. So all the secrets satisfy these conditions, we will call them as small secrets. And the crucial point concerning the small secrets is that all small secrets on the same rosy graph are independent. Here, let me just clarify what I mean by small secret. Let us just consider the example I showed you just before. If we let W be a word like this, and its third rosy graph is like this, well, we can find on this graph there exist at least three secrets. The first one is this one. We begin with BAA, and we go through AAB and ABA, and we return to the word BAA. So this is a secret. This is a secret and the number of edges on this secret, which equals the number of vertices on this secret equals 3. As 3 is upper bounded by 3, so this secret can be considered as a small secret. And similarly, there exists another secret. As the number of vertices on this secret equals 2, so this secret is also a small secret. But besides of these two secrets, there exists a third one, is a large one. We begin with BBA and we go through BAA, AB, ABA, BAA, etc. We return to BAA. So on this secret, there are 7 different edges and 7 different vertices. As 7 is larger than 3, so this secret cannot be identified as a small secret. So with the property that the image of phi are all small secrets, and the small secrets on similar radial graph are independent, we are almost at the point to conclude. In fact, if we count just the number of images of phi on the radial graph gamma I, then we can say that this number will be bounded by the chromatic number of the graph gamma I, which equals Ci plus 1 minus Ci plus 1. And if we sum up all these inequalities for all i's from 1 to the length of w, then as the left-hand side, we will get exactly the total number of distinct non-empty squares appearing in W. And on the right-hand side, we will have the length of W minus the size of its alphabet. So the proof is completed. Well, here I will just show you an example how our theory works on the particular word W that we have that had been shown before. If we let W be a word like this, then first of all, the 2 squares BB and AA will be identified respectively to these 2 small secrets. Remarking that on this radial graph, there exists another secret like this, whereas this secret contains 2 different edges where we are on gamma 1. So this secret is not small. So this one cannot be associated with any squares. And for the word ABAB, we will switch to gamma 2, and the ABAB will be associated with this small secret. And we remark that on this radial graph, there exists one more small secret like this. Well, this small secret will not be associated with any squares. The word BABA will be associated with this small secret on gamma 3, and the word ABA will be associated with this small secret on gamma 3 as well. On gamma 4, there exists one secret like this, but this secret is not small, so it will not be associated with any squares of W. And on gamma 5, there exists one more a small secret, and this small secret will be associated with the word BABA. And on gamma 6, there exists a secret like this, a small secret like this. This one will be associated with the word ABAB and ABAB. And up to now, all the square factors of W are associated with one small secret on the radial graph, and we can see that all these small secrets are independent. Thus, our theory works well on this particular example. So once we give a new upper bound of S star of W, the first question we may ask is that, is this upper bound sharp? Well, the answer is no. The upper bound of length of W minus its alphabet is not sharp. In fact, there are three different reasons. First of all, there exist some gaps. Here, let me explain what I mean by the gaps. If we let X be a word A, B, and we let W be a word containing X powers 4 as a factor, then from our previous construction, we can associate the word AB squared to a small secret on gamma 3, and ABA squared to a small secret on gamma 4, and the BA squared to a small secret on gamma 5. Well, for the AAB powers 4, we associated it to a small secret on gamma 9. However, there are similar secrets on gamma 6, 7, and 8 as well. Because on gamma 6, we can easily check that there exists a small secret like this, and on gamma 7, there exists a small secret like this, and on gamma 8, there exists a small secret like this. So that is to say, we haven't constructed an injection from, we haven't constructed a bijection from the set of squares to the set of small secrets. So there are many small secrets which are not associated with a square. In fact, from this point of view, we can make a generalization of our previous result. If we define the power of a word to be a word of the form U powers k, which consists of k copies of the factor of the word U, and we can and if we let the capital M star of W denotes the set of all non-empty powers of U with an exponent at least 2. By the exponent, I mean just the index of the power. Then, in fact, we can make a better injection, which associated all the non-empty powers in M star W to the set of small secrets on the Rosy graphs of W. So as a generalization, we can prove that the total number of distinct non-empty power of exponent at least 2 can be bounded by the length of W minus the size of its alphabet. Moreover, if we let mk star denotes the number of distinct non-empty k powers of W, then the mk star of W should be upbounded by this value. So this result can be considered as a generalization of our previous result. However, the reason why is not critical, because we may able to construct words which do not contain any other powers of exponent at larger than 2. So in this case, we may not expect it that we can always have the gaps. However, there exists a second reason. In fact, if we consider on the Rosy graphs, we can find there exist other secrets which are independent with the small secrets. In fact, let's consider always our example with x equals AAB and x and W is the word containing x squared as a factor. Then we can find the following secrets on the graph gamma 2 such that all its edges are the conjugate of W of x. All its conjugate of these secrets are no, sorry. All the edges of this circuit are conjugate of X. So if we consider this circuit, we can conclude that it is not a small circuit. And I would like to call them a primitive circuit. Here, let me give you a exact definition of what I mean by primitive circuit. If we let W be a primitive word, and if we let X be a primitive word, and if X squared is a factor of W, and the length of X is larger than or equal to 2, then there exists a circuit on the graph gamma with the index length of W minus 1, such that its H set is all conjugate of X. Then this circuit is called a primitive circuit. And the crucial point is that all primitive circuits are independent with the small circuit. So if we add the number of primitive circuits and the number of small circuits up, the total number will be upper bounded by the length of W minus the size of its element. So this is the crucial point to say that the upper bound of length of W minus the size of this alphabet is not sharp. Besides of this, in fact, there are some simulations which has already been done. In fact, we can find the sequence A24, 89, and 55 on OEIS, which counts the maximum number of distinct non-empty squares in a binary string of length n. Then the sequence then the first elements of this sequence are listed as above. So we can easily check that this sequence increase merely slower than the linear function fx equals x. So in fact, we can give a better upper bound for this sequence, which leads to our new conjecture concerning the number of distinct squares in a word. If we let ms denotes the maximum number of distinct non-empty squares in a word of length w, then we conjecture that ms should be upper bounded by the function n plus 1 minus square of n minus log 2 of square of n. We remark that the sequence Bn are only calculated for binary words, where our conjecture are made for words with arbitrary alphabet. In fact, if we compute the difference between our new upper bound with the sequence Bn, we will get the following sequence like this. And we can easily check that, first of all, this sequence is non-negative. So which is evident that our upper bound may be a good one. And another observation of this gap is that this sequence is increasing slowly. So for the first terms, these two our new upper bounds match well with the Bn, and if n is large, maybe there will be a gap between our new upper bound and Bn. So maybe there maybe our new upper bound maybe can be improved, but for now we think it is already a strong conjecture, and I have, for the moment, I don't have any ideas about proving this. So besides of our this new upper bound, we may make other remarks and on the square counting problem. For example, if there exists some word W satisfying that the number of squares appearing in this word meets exactly the theoretical upper bound of MS, then can we say the word W is necessarily a binary word? Well, this question has been asked by different people at different time, but for now it's still open, and so I'd rather list it here. And next question is that if we consider the sequence MS itself, can we see just the difference between two consecutive elements of the sequence are upper bounded by 1? If we check the sequence Bn, this conjecture works well, and if the sequence MS is exactly the sequence Bn, which means the first question is verified, then the second, then we may expect that the second one is also true. And besides of these questions concerning the square counting problem, we may ask other problem concerning the topological properties of the Rode graph. For example, can we compute exactly the number of independent sequences on Rode graph? Because from our previous argument, we were working on the small sequence, and we show that the small sequences are all independent. However, there are other sequences which are independent with the small sequence, for example, the primitive sequence. And are there any other sequences which are independent with these two type of sequences on Rode graph? Well, this question is still open for me. Maybe you have the answer for this question, but it's an open question for me. So at the end of the talk, let us just reveal the motivation of our research. And here I would like to explain why we would like to prove the Franco-Simons conjecture with this formula, and where is the term, the set of alphabet of W from? Okay, in fact, this is from observation of Brilec when they trying to doing some analog works with his previous works on palindromic defects and sigma palindromic defects. In fact, the palindromic defects as well as the sigma palindromic defects are defined as follows, which equals the length of W plus 1 minus PW as well as P sigma W. And it was proved that for any finite word W, the palindromic defect as well as the sigma palindromic defect satisfy these identities. These identities are known as BR identity with the name of Brilec and Hertenauer. Here, in terms of PWI as well as P sigma WI, we mean respectively the number of distinct lengths I palindromics in W as well as the number of distinct lengths I sigma palindromics in W. So if we define the square defects of a word in a similar way, and we consider the BR identity for the square defect. If we can prove the following, we can prove that the BR identity for squares also holds for all finite words. But if we reformulated the square defect, the square BR identity a little bit, we will get an equation like this. And if we want the square defect to be positive, then we will expect that the number of squares should be upbounded by this number. So this inequality is equivalent to see exactly the number of squares where W is upper bounded by the formula that we have just proved. Moreover, the Frankel-Simpson's conjecture is equivalent to see that the square defect is always positive. So once we defined and studied the square defect for finite word, we can also define it for infinite word. If W is an infinite word, where the square defect of W is defined to be the superior of the set of all DSP, where P are factors of W. In fact, it is already proved by Birkel-Dawes and Van Dam that the square defect of any infinite periodic word and the strict standard epistemic word are infinite. Moreover, the BR identity also holds for these two types of infinite words. And at the end, we will conclude my presentation by giving two conjectures. One is that the square defect of any infinite word is infinite, while the square BR identity holds for any infinite word. So that's all for today, and thank you for your attention.
Oh, thank you very much, Shuo. Does anyone have any questions?
May I ask?
Yeah, Arseny, go ahead.
Yeah. Thank you very much for very nice talk, very nice results. I can just add maybe one more question to your list. I can add such a conjecture. Suppose you have a K-ary word with the maximum possible number of squares for a K-ary word. Then the conjecture, which is supported up to some extent by direct computation, the conjecture is that all squares in this word are binary. So the word itself is K-ary, but if it contains the maximum number of squares among K-ary words, that all squares are binary. So each square is a binary or unary, of course. But,
so good point.
Yeah, so maybe it somehow fits the other questions, so maybe it will be easier to study them together.
Yes.
With the other one. So
yes. It would be a good question. Thank you so much for your remark. I will think about it. I have never thought about this. And thank you for the.
Are there any other questions? So Shuo, is it true that in the previous results on this problem, nobody was using rosy graphs before? Is that true?
I don't know from the literature, it seems to be so, because if we use it, the result would be straightforward. So when I read the previous work, I don't find any.
So you were the first one to try it.
Maybe. In fact, if we consider, let me show you something. Wait a moment. When I talk about the BR conjecture, no, the PR identity. Yes. So in fact, when people working with this formula, in fact, we are proved that it is proved that for any finite word, each term like this are positive, and it was proved by using the Rosy graph, but not in the same way that I used. So yes, the briefly speaking, the BR conjecture has been no, the Rosy graph has been used to solve some of problems like this, but not to being used to study squares. Yeah.
Christophe has a question.
Yes, I think Shuo Li has just answered the question, but I ask anyway. In your formula, which is on the slide now, on the on the board, is each term, I mean, in the sigma, term positive? I mean, the 1, 2, 3, 4, 5. The sum of the 5 terms is always non-negative.
Yeah. For this question, I don't know. For the sigma Benjamin, yes, I don't know.
No, but because you the defect of an infinite word is infinite, and
yes,
and you also that the BR generalization is true, but it's an infinite sum of
it's an infinite sum of this.
So you mean that at the left it's infinite, and so at the right it's also infinite, but it's an infinite sum of integers. So I think
maybe we may have some negative.
So each term should be positive, otherwise I don't know.
In fact, if the index is large enough, then it would be positive. But for small integers,
okay,
I don't know.
Okay, that's fine. So for I large enough, the terms are non-negative, and perhaps the first term are not. But this doesn't change for the convergence. I mean, the conversion to infinity. It's better to yes. Okay, thank you.
And thank you.
And just a remark. This conjecture of Arseny Shuo is really incredible. I find it's some structural property of. If I just say it again, because if to know if I understood well, he takes a k-ary word, which the maximum number of squares. Then he says that all the squares appearing are binary words. So this is a very strange conjecture. I mean, it's strange because I don't understand, but it's extraordinary if it's true, because it means these words have some structure. Special structure.
It should be. I haven't thought about this, but it should be.
Anyway, thank you.
Thank you.
Robert?
Hi, so I'm not sure, can you hear me?
Yeah, sure.
Okay, so I'm not sure if I understood Arseny's question correct, but I think that Desafranek and Thierry gave a word which is gave a ternary word of length 33. which basically has one square extra than any binary word. And the trick is, if you're looking at the sequence, the AOS sequence that you gave, Shuo, the idea is that at some point, the numbers actually repeat themselves. So basically, if you increase the length by 1, the number of squares will not change. And I think that basically, if you do that 3 times in a row, and I think you get it around 33. If you do this 3 times in a row, what you can do is actually erase the last 3 letter symbols in a way and just add a CC at the end. So in this way, you get like a non-binary square for free, so to say. So basically, the word of length 31 has the same number of squares, or 30. No, 31 with 33, I think it is. And what they do is, well, they consider the word of length 31, the binary word, just add CC at the end, and then you will get word of length 33, which has 1 extra square.
I see. So,
But yeah, asymptotically, it was Mana and Seki who showed that basically if you have a certain square density that you can achieve with a k-array word, then you can also achieve the same square density by constructing, by giving a constructive proof for a binary word. So that means that their binary word will be much larger, but in the end, asymptotically, we'll get the same square density.
So do you think the size of the suffix we add would be bounded? So, I mean, it's always something like CC we would add at the end of a word.
So I think that for words, for binary words, you can always achieve the same density, so to say, in the number of squares as for a bigger size alphabet. But at points, it might be that according to the Deza, Franek, and Thierry, I think it is, observation, you will always get a word on a higher alphabet that will have more squares, like 1 extra, that you can construct this artificial way. So, or so it seems. That's it. It was more of an observation. I'm not sure if it's if I understood something wrong and it's not correct what I said.
Arseny, did you want to say something?
Yes, I should just know that what was said by Robert. So if you can add as instead of 2 last letters of the binary word, you can add CC and get 1 more square, but still the square you added is a unary word. So it does not contradict to my conjecture. I don't suppose that all these squares should be all over the binary alphabet. Just each of them is a binary word or unary word.
Okay.
So
I got it wrong.
Possible. It's still possible to be true.
Right. So each square is over 2 letters. You don't know what 2 letters, but 2 letters. All right. Does anyone have anything else? If not, I'll say thank you to Shuo again. Very nice talk. Very good results.
Thank you. So,
and our next talk will be in 2 weeks, and we'll have Robert Fucking.